Good day, everyone. In this video, I will going to discuss about work and energy. In this module, I will going to discuss to you on how to use the work and energy equation in order to determine the displacement, the velocity, and the acceleration of a given system of rigid bodies undergoing rotational and translational motion. In the previous modules, you have learned the method in calculating those parameters by using the force inertia method developed by Newton. This time, we will use another technique in solving those parameters. So this is according to the Lagrange method that is all about work and energy. Your takeaways for this lesson is first, you will be able to understand the fundamental work energy equation applied for both translational and rotational. As a review, when we say translational, this is a type of motion of a certain object that moves on a straight path, whereas for rotational, this is a type of motion for a given object that is rotating about a fixed axis. The second one, you will be able to apply the fundamental work energy equation for translation and rotation in solving systems of rigid bodies undergoing translational and rotational motions. Now let's start with the concepts and derivation of the work energy equation applied for translational motion. So that is a given rigid body or an object is undergoing a straight line motion. So the work energy equation for translational is being derived from these two equations in dynamics. So these are, the first one is the Newton's law of motion, that is the summation of forces or the resultant force will result to an acceleration of the object. So weight over g here is the mass of the object. So this is our first equation to be considered. Then the second one is, this is the differential equation that is being derived from the kinematics equation, in which the acceleration multiplied by the change in the displacement is equal to the product of the velocity multiplied product of the velocity and the differential velocity or change in the velocity. So we are going to manipulate these two important equations in dynamics in order to arrive the general formula for work energy. Now in equation 2, we are going to solve for the acceleration in terms of the velocity and the differential velocity and differential displacement. Again, S here stands for the displacement of the object. The acceleration is equal to v dv over ds. Now we are going to substitute the expression for the acceleration to our first equation right here. So it will now become summation of forces is equal to the mass, this one, multiplied by v dv over ds. Next is we are going to multiply both sides of this equation by ds. It will become F summation of forces times the differential displacement is equal to mass times the velocity multiplied by the differential velocity. Next, we are going to integrate both sides of the equation because this equation is a differential equation. So in order to um, get the general solution for this one, we are going to integrate both sides of the equation. So we have the integral of the summation of forces multiplied by the displacement that is evaluated from 0 to the final displacement s is equal to the integral of mass times the velocity multiplied by the differential velocity and is evaluated from the initial velocity v naught to the final velocity v. Integrating this, especially on the starting with the right side of the equation, so we have here 1/2 wg v squared from initial to final. And if you're going to simplify this, it will look like this expression. So this is the expression. This is very familiar because this expression is the kinetic energy of a rigid body. Now, if we consider that the forces, summation of forces acting on a body are constant, therefore the expression above right here will become summation of forces multiplied by the displacement is equal to 1 half W over G, the mass, multiplied by the square of the final velocity minus the square of the initial velocity. Now, on the left side, this is the formula for our work, which is the product of the force and the displacement that is equal to the right side of our equation. So the expression on the right side of our equation talks about the kinetic energy of a moving body. That is a function of its initial and final velocity. So we call this as the change in the kinetic energy of a particle. For work, these are the points that you need to consider. So for work, we have here a force multiplied by the displacement. See to it that the force must be parallel to the displacement, because if the force is oriented perpendicular to the displacement, there is no work done on the system. So force and the displacement, both are vector quantities, must go along. That is, they must have the same direction. Or if it is uh, not necessarily the same direction, but both of their vectors, the line of action for both vectors must be the same. Okay? Now, uh, we are going to apply the work energy equation for a given system of body. But this time, we will consider only one object. So we have here an object, and let's say this object is moving towards the right, and it has an initial velocity v naught. Now, in maintaining this initial velocity, of course, we need an applied force. Let's assume that Fa is the applied force, which is constant. So um, this one is responsible for maintaining the speed of this object, v naught. Now, suppose we have a friction that exists between the block and the horizontal surface. So this frictional force Ff opposes the direction of our applied force, and in turn, it reduces the speed of our object. So let's say this is the initial position of our object, point 1. Now, at point 2, so since we have a frictional force, a constant frictional force that is being applied other than the applied force, we will expect that at the second position, its velocity will change. And of course, since it is in motion, it has a displacement equal to s. So it moves at a certain distance towards the right. Now, since we have a frictional force, so the velocity of this object changes from v naught, that is its initial velocity, towards v, which is its final velocity. Now, in this diagram, we are going to quantify the amount of mechanical work done on the system, and we are going to let this as small w in order to not be confused with the uh, big letter W for the weight of the object. So we will use the small letter W. Now, the work that is being done on the system from point 1 to point 2 is equal to, again from the previous slide, that is equal to the product of the resultant forces multiplied by the displacement. As you notice, I put here some sign convention. So it is positive, the force is positive if it is oriented towards the right. So the sign convention for the direction of the force indicates that the force is positive if it points towards the right. Why is it? It's because we align a positive work if it points towards the direction of motion. Now, in our diagram, the direction of motion is towards the right. So if the force is oriented in that direction, that is towards the right, so that force produces a positive work, because in the concept of work, we have two types. We have the positive work and the negative work. Now, do not be confused with the sign. It's because maybe you will think that this signs is the same as the vectors. Take note that the concept work is not, or the quantity work, or the physical quantity work is not a vector quantity, but a scalar. So the sign only means that if we have a positive work, the work done is on the system. So the work is done on the system. But if we have a negative work, so this force does not help the object from moving from one position to the other. So the negative work will decrease the uh, the energy that is available on the system. That is why if we have a negative work, it's either the velocity of the object will decrease. So the sign convention here will help you to know which of the forces that are given on the system are positive or negative, or which of these forces will create or contribute a positive work, or which of these will contribute a negative work. Now, in our example, the applied force, as you can see, is directed towards the right. So this applied force helps increase the velocity of our object, or it helps the object in moving from point 1 to point 2. Now, we have here another force, which is the frictional force. The direction of this force is opposite to our direction of motion. So therefore, it creates a negative work, meaning to say it reduces the velocity of our object, or it diminishes the available energy that is present on our system. Now let's go back to our equation right here. So if we follow the sign convention, and if we take the summation of forces, from our diagram, we only have two forces that are aligned with our direction of motion. By the way, we did not consider the work, the weight, and the normal force. Okay, I did not consider the weight and the normal force right here, because these two are oriented perpendicular to the direction of our motion. So it does no work on our system. So we only have two forces right here, the applied force and the frictional force. So we have here Fa minus Ff times the displacement. So both of these forces have the same displacement, and that is equal to S. Again, the negative here indicates that the frictional force does a negative work on our system, which means that it reduces the speed of our system. Now, if we're going to simplify this one, so distributing the S, we have the work done from 1 to 2 is equal to Fa times S minus the frictional force times the displacement. So the change in kinetic energy in the system, that is delta Ke, is equal to 1/2 W over G multiplied by the square of the final velocity minus the square of the initial velocity. So therefore, the work done on the system is equal to the change in its kinetic energy. Of course, this is from our work energy equation. So we equate both of these expressions. We have the summation of forces times the displacement. So this is for the work. And on the right side, we have 1/2 m v final squared minus v initial squared. So the final expression for this system is equal to Fa times S minus Ff times S is equal to 1/2 W over G times the difference of the square of the final velocity and the initial velocity. Now, if we don't have a frictional force, of course, our final velocity will also change. Again, The negative work indicates that um, it diminishes or it reduces the available energy that is being present in the system, and that is in terms of the kinetic energy. So only kinetic energy are or only the kinetic energy is being considered in this system, assuming that there are no heat losses or other forms of energy that is being present or that are being present in the system. Okay, let's have um, another diagram. So let's say that the weight of our block C is greater than the sum of the weight of blocks A and B. So this type of system is a multi-body system because it comprises of three blocks that are connected by this rope, and we also have a pulley right here. We will assume that this pulley is frictionless and weightless. Now, if the weight of our block C is greater than the sum of the weights of A and B, so most likely the block C will pull this these two blocks A and B in this direction. So this is the direction of our motion. Again, this is not or the amount of force that uh, does the work here for our multi-body system uh, is not the work, or I mean is not the weight of our block C, but rather uh, its parallel component only. So we have here W parallel C, meaning the parallel component of our weight, because remember the weight here is oriented uh, downward. Now, another forces that are present in our system, starting with block C, we have the frictional force. We have FFC. The direction of the frictional force is always opposite to the direction of our motion. That is why it is uh, pointing upwards. And we also have a, a tension that exists between or a tension that exists on the ropes that connects block C and B. If we have a frictionless pulley right here, so we can assure that the tension on block C and on block B is equal or are equal. So we have here T2 and T2. Next, we also have a frictional force FFB that exists on our block B, and we also have the tension on the rope that connects A and B. And lastly, for our block A, we also have a frictional force FFA that is directed opposite to the direction of our motion. And as the weight or the parallel component of the weight of block C pulls this system, so it has displacement. So for block A, we have here SA. For B, we have SB. And then for C, we also have here S sub C. Now for multi-body system, the amount of mechanical work done on the system is equal to the summation of the individual works for every object that are present in the system. So we have the work for A plus the work for block B, and then plus the work for block C. And then we will use the formula for the work done, that is summation of forces times S for A, B, and C. And don't forget to indicate the, the sign convention. So we take positive if the force is along the direction of motion. So in this case, that is towards the right. Next, the summation of forces that exist for block A, we have a tension T1 minus the frictional force at A times the displacement of A, plus for block B, we have three forces present. These are T2, so T2 is positive, then FFB is negative, as well as T1, then multiplied by SB. And lastly, for our block C, we have three forces. the parallel component of the weight of block C minus the frictional force minus the tension on the rope that connects block B and C. Next, we are going to simplify this one, but before that, uh, we are going to consider this assumption. So if the bodies as well as the connectors are rigid, meaning it doesn't have any elongation, or the ropes or the connectors does not elongate as the system moves, so we can say that the displacement for block A is the same as the displacement of block B as well as block C. And if that is the case, so we will assign the displacement of each blocks by simply this small letter S. Next, we are going to substitute this one in our equation right here. So it will become T1 minus FFAS plus for block B and for block C. Then distribute the displacement to each of the terms inside the parentheses, and you will end up with this expression. And as you can observe, we have some terms that can be cancelled out. We have this one to be cancelled out with this one. And what else? We also have this one minus this one. Okay. And I think there's nothing more. So therefore, the total work done on the system is equal to the negative of the frictional force at A times S minus for the frictional force of B plus the parallel component of the weight minus the frictional force at C multiplied by the displacement. Next, we are going to rearrange this one. So the amount of work done in the system is equal to the parallel component of the weight of block C multiplied by the displacement minus the negative uh, work or negative works that are present in the system. That is the frictional force that exists at block A, then at block B, and at block C. If we don't have any frictional force, so what is only present is the parallel component of the weight C. And this one is responsible for moving the system in the direction of the motion of the object, which is directed towards bottom right. Now, uh, what we can observe as we derive its formula is that the internal forces present in the multi-body system, such as the tension T1 and T2, do no work since these are cancelled out during the solution process. So next time, if you will meet a multi-body system with connectors, so do not um, include that one in your calculation for the work and energy equation, because if you are going to refer our derivation, we have just um, we have just noticed that the internal forces such as the tension that exist on any connectors will be cancelled out. So do not include those internal forces if you use the work energy equation. Consider only those external forces such as uh, the weights of the objects that are present, as well as the frictional forces that exist for all the objects present on a given system. Next, aside from the work, we'll also consider the change in the kinetic energy for a multi-body system. So the total change in the kinetic energy of a multi-body system is equal to the summation of the change in the kinetic energy for each objects that are present for a given multi-body system. So we have the change in the kinetic energy for block A, then for block B, and then for block C. Now, we all know that the formula for the kinetic energy is 1/2 mass times the difference of the square of the initial and final velocity. So this is the expression that I am talking. So the first term is for the block A, the second term is for block B, and then the third term is for block C. Now, if the bodies as well as the connectors are rigid, So we can say that uh, their displacement are equal. And then we can also say that the initial velocity for blocks A, B, and C are also the same. So instead of having these parameters, we'll assume that the initial velocity of these three blocks is equal or denoted by V naught. And for their final velocity, we will just denote uh, them as V. Okay? Now, we are going to substitute these two parameters. So this will be the outcome of the expression for the total change in the kinetic energy of the system. So for the first term, this one is for block A, for the second term for block B, and then for the third term, this one is for block C. Now, the total change the kinetic energy of the system, since the difference in the velocities for all terms are the same, so we can factor this one as well as the 1/2 times 1 over g. So we have here 1/2 times the square of the difference of the square of the initial and final velocity all over the acceleration due to gravity g, multiplied by the individual weights of blocks A, B, and C, multiplied by the sum of their individual weights. Now, combining the work done on the system and the change in the kinetic energy gives us the work energy equation. So total work is equal to the total change the kinetic energy of the multi-body system. This one is the resulting equation, work energy equation, that is applied for this kind of system. Class, this is not yet a fixed formula. It's because this formula depends on the given multi-body system. So this one is only applicable for this kind of system considering this assumption. So we have, if the weight of C is very uh, very large compared to the sum of the weight of block A and B, and then if the bodies as well as the connectors are rigid, so we can assume that these three blocks have equal displacements, as well as their initial velocity also equal and the final velocity. But this one will apply for all types of multi-body system, because this is of course the general equation for work energy applied for translation. Now let's have some example. So number one, determine the velocity attained by block A in the figure shown after moving a distance of 12 feet starting from rest. Calculate also the total change in the kinetic energy of the multi-body system. So this is our multi-body system. We have a 300-pound block B that rests on this inclined plane, whose inclination is equal to this triangle, wherein its run is 3 units, and then its rise is 4 units. And then this block B is connected via a compound pulley towards our um, block A, whose weight is equal to 400 pounds. And the inclination of this surface where our block A rests has a run of 4 units and a rise of 3 units. And the coefficient of kinetic friction that exists between the blocks and the inclined surface is equal to 0.2. Now, these are the given parameters for this problem. The weight of block B is 300 pounds. For A, that's 400 pounds. The given coefficient of friction, kinetic friction, is 0.2. Then the displacement of our block A is 12 feet. And if you're going to read the problem statement, we have there a phrase that states starting from rest. It means that the initial velocity for both blocks A and B is equal to 0. Next, we will proceed to the requirements of this problem. Uh, these are the requirements. First is we are going to solve for the final velocity of block A after moving a distance of 12 feet starting from rest. And the second one is we are going to calculate the uh, total change in the kinetic energy of the system. So the method to be used here is we're going to use the work energy in solving both the final velocity of A and the total change in the kinetic energy of the system. So we can use the work energy here. It's because the requirement is the velocity, and we all know that one of the variables that are present in the work energy that is present in the work energy is the velocity. Okay, so first step is we are going to generate the FBD of our multi-body system. It is called a multi-body system because we have two blocks that are present in our system. So this is our system. As you can see, these are the direction of motions. So why is it that the direction of motion for block B is pointing towards bottom left or down the inclined plane? It is because the from the previous slide, since the weight of block B is great, although in numerical value is not greater than A, but since we have an inclination here, and since uh, we have a compound pulley right here, so if this is a 400 pounds, most likely the horizontal component of the weight for block A is a little bit smaller than 400 pounds. And since we have a compound pulley connection right here, so the horizontal force of block A will be split, or will be divided into two. So it will be less than the horizontal component that is being generated on block B. So therefore, for this system, block B has the ability to pull our 400 pounds block A on the right side of our system. That is why the direction of motion for our FBD, especially for block B, is directed towards bottom left or down the inclined plane. And for block A, the direction of motion is oriented up the inclined plane due to this compound pulley arrangement. Next, we will consider the forces that exist on our block B. So we have the weight of the block B, the frictional force shown by this red arrow. So this is FFB. And as you can see, the frictional force is always opposite to the direction of motion, because that is the purpose of friction, which resists the object from uh, moving, or uh, it is opposite to the direction of the applied force. And we also have the normal force that is being exerted by the inclined surface. And then if we are going to indicate the inclination of this plane, so we have a uh, 3 units run and 4 units rise. So the hypotenuse of this one is 5. Now we're going to use this one in order to get the components of this weight, which are normal, that is 3/5 of WB, because if this is theta in our um, FBD here, this is this one, the angle here is also theta. And then the parallel component of the weight of block B is equal to 4/5 WB, because this side is opposite to our angle, so we take the sine of this triangle, that is the ratio of 4 and 5. Next, we also have a tension that exists on our block B, so we have here T. And then for the compound pulley arrangement, so if this is T, this is also equal to T. So therefore, the amount of tension that is being exerted on block A is equal to twice the tension. So we have here 2T. Next, we'll proceed to the FBD for block A. As you can see, we have its weight. Then we have the frictional force for block A. Since the direction of motion is up the inclined plane, so the direction of this frictional force is down the inclined plane. And we also have a normal force for this one. Okay, so this is our normal force. Now, if we're going to use this um, triangle, by the way, this is um, this this diagram is used to determine the inclination of this plane. So it has a 4 unit run and 3 unit rise. So these are the components of the weight of our block A. So the normal component of this weight, or the weight of our block A, is 4/5, and then its parallel component is 3/5. Now, next is we are going to solve for the frictional force FFB, starting with FFB. So if we take summation of forces on block B, that is on the normal axis, that is the axis perpendicular to this inclined surface, that is equal to 0. And we take the positive force if it is oriented um, towards top left, as depicted by this arrow. So we have the normal force NB is equal to the normal component of the weight of block B, that's 3/5 WB. Next, the frictional force is equal to, again, the product of the normal force and the coefficient of friction. So substituting the values, we have zero point 0.2 for the frictional force. I mean, the coefficient of friction, kinetic friction. Then we have 3/5 times 300. So we have a frictional force on block B equal to 36 pounds. Next, we will proceed to the frictional force at A. By the way, this is not frictional forces. This is only frictional force. Sorry for the typo. So we take summation of forces normal to our block A, that is equal to 0. So we take positive if it is directed towards top right. So this is not the correct arrow, but rather this one is the correct arrow. Okay, so sorry for that. Next is the normal component. I mean, not the normal component, but the normal force at block A is equal to the normal component of the weight of our block A. So we have NA equals 4/5 WA. Next, the frictional force at A is equal to the product of the coefficient of kinetic friction and the normal force at A. So we have this expression. Next is substituting the values. So we have zero point 0.2 for the coefficient of friction times 4/5 times 400. So the weight of block A is 400. So after that, if you're going to input this one in your calculator, you will arrive a value for your frictional force equal to 64 pounds. Next, we will determine the relationship for the displacement as well as the velocity of block A and B. So this is very useful, especially when dealing with or when working with the work energy equation. It's because for the work energy equation, you need only one unknown in order to solve those requirements. It's because if you have two unknowns that are present on your work energy equation, it is impossible for you to solve those unknowns if you don't have another equation for that, because for the work and energy equation, there is only a single equation. So for a single equation, you only have, or you should have one unknown in order to solve for that one. It's because if it is two or more unknowns for a single equation, you cannot solve that one. You need um, more equations for that. Okay, so let's go back to the relation of the displacement, the velocity of A and B. So how are we going to get its relation? So since we have a compound pulley arrangement right here, as you can see, if block B moves 1 unit downwards, so the movement of A is half of B. It's because of this compound um, pulley arrangement. So which means that for every 1 unit that is being moved by B, so it will uh, take uh, one full turn for this pulley. So 1 unit on this side and 1 unit on the other side. So that is why um, for every 1 unit of displacement of B, that is only half of A. Or in other words, the displacement of B is twice the displacement of A. That is why we have this equation. So this one is due to the fact that um, the arrangement, the pulley arrangement that is present in our system is compound. It's because of this section right here. So SB equals to SA. Now, if we differentiate the given equation with respect to time, we have the displacement over time, that is the velocity. So we now have a relation for the velocity of A and B. So the velocity at B is also twice the velocity at A because of this compound pulley arrangement. Now, we will proceed to the work energy equation in order to solve for the requirements of this problem. So the total work done on the system is equal to the total change in its kinetic energy. So since we have two objects present, these are block B and block A. So we have the work done on A plus work done on B. That is equal to the change in the kinetic energy of A as well as on B. So for the work done, now starting with block A, this one right here. So as you can see, we have negative 3/5 WA. So why is it negative? Okay. By the way, before we proceed to this one, going back to our FBD, we have some color codings being used right here. So the force vectors labeled or colored in green does not produce any work. It's because um, they are not oriented parallel to the direction of motion. So for the case of the weight, so the weight here still has its component um, who does work, and that component is the parallel component of the weight. That is why if you have a force that is not perpendicular, that is um, it is inclined at a given angle, for this case angle theta, you should um, find its component in order for you to know which of its component produces work. So in this case, the parallel component of the weight of this block B produces work. Okay, so the tension here is not part on the solution for the work and energy. It's because these are internal forces. So we are only aftering with the external forces. So these are the components of the weight as well as the frictional force. Now let's go back to the work done on block A. So we have here negative 3/5 work A. This is negative. It's because, as you can see, this force right here is opposite to the direction of our motion. Then we also have minus FFA. So FFA is very obvious. This is opposite to the direction of motion. Next, we'll proceed to the second term on the left side of our equation. This is the work done on block B. So on block B, we have a positive work for the parallel component of its weight. So this is 4/5 of weight B. So you can see the direction of this component, this weight component is along the direction of motion. Then we also have minus the frictional force at B. Then that is equal to the change in the kinetic energy for block A and for block B. Next, we will consider some assumptions. So in the problem statement, we have there a phrase starting from rest. This means that the initial velocity for both blocks is equal to 0. Now we are going to substitute this one right here in our equation, as well as the displacement and the velocity relations. So the displacement of B is twice that of A, and same goes with the velocity. So the velocity, the final velocity of B is twice that of the final velocity of A. So we are going to implement these three conditions. So the work energy equation becomes, or it will look like this equation. So the only modifications that happen here are the the expression for SB. So this time SB becomes 2SA, and then the initial velocity for both A and B are now 0. So substituting the values, so the weight of A is 400, then the frictional force at A is 64, then the displacement of A, as stated in the problem, that's 12 feet, then the weight of B is 300, the frictional force at B is 36, then twice the displacement of block B is twice that of A, so we have here 2 times 12, then equal to 1/2 times the weight of A, that's 400, all over the value of the acceleration due to gravity of the earth in feet per second squared, that is 32.2, then multiplied by the velocity, the final velocity of A squared, plus 1/2 times the weight of B, that's 300, all over the earth's acceleration due to gravity, times here we have 4. So why is it? It's because we have a relation that the velocity of block B is twice that of A. So we have here again, uh, the velocity of B is twice that of A. So we have 2VA squared. If we're going to simplify this, you have 4VA squared. Next, simplifying the left side of the equation, it will become negative 3648 plus 4896 is equal to this one. Now, we can combine these two terms. So we have 1248 is equals to 4000 over 161 VA squared. Next, divide both sides by 4000 over 161. So you have here VA squared is equal to this expression. Then square both sides of the equation. You will have a value for the final velocity of A that is roughly equal to 7.09 feet per second. Next, we are going to solve for the total change in the kinetic energy in the system. That's delta KE total. So you can use either the formula for the total kinetic energy, that is in terms of the weight and the square of the initial and final velocities, or you can also use the formula for the work done on the system, because both are equal. So in my case, I use the uh, formula for the work done because it is much easier compared to the kinetic energy. So I have here negative 3/5 weight of A minus the frictional force times the displacement of A plus the expression for the work done on B. And as you can see right here, I already substitute the expression for SB, that is equal to twice of SA. Now substituting the given values for these parameters. So the weight of A is 400, the frictional force at A is 64. We already solved this one from the previous slide. Then the displacement of A is 12, then the weight of B is 300, the frictional force at B is 36, then the displacement of B is twice that of A, so we have here 2 times 12. Now, I'm simplifying these terms on the right side of our equation. So we have the total change, the kinetic energy is equal to negative 3648 plus 4896. So we have a total change, the kinetic energy of the system equal to 1248 foot-pounds. So we have a positive work, total positive work on the system. So this total work increases the velocity starting at rest, that is at velocity equal to 0, to the final velocity of A, that is roughly equal to 7.09 feet per second. Now let's proceed to our second example. We have here a particle of weight W. This one, we have a particle moving with a velocity of v naught. So this is used to denote the initial velocity of our object. So at A, so in this position, slides vertically along the surface of a smooth cylinder of 8 feet radius as shown in the figure. So it slides from this position at point A towards point B, and it has an angular displacement of 30 degrees. For this smooth cylinder, the radius of it is 8 feet. Now, it leaves this surface at B. So the moment that this particle reaches at point B, so it is now leaving this cylinder. Now the question is, first, so we have two requirements. First is determine the initial velocity v naught, then measured from the center of the cylinder, how far will the particle travel horizontally before it strikes the ground? What does it mean? So in our diagram right here, what it means is that the horizontal distance measured from the center of the cylinder towards the point where it strikes the ground, and that is our x in our diagram. So we are going to list the given parameters. So the weight of the particle is equal to W in pounds, and then the radius of the cylinder is 8 feet. I think um, these two are the only given aside from the 30-degree angle. So the requirements for this problem are the initial velocity of our particle and then the displacement x, as you can see from the illustration. Now the method that we're going to use is that first we're going to use the work energy method applied in curvilinear motion in solving the initial velocity v naught of the particle and the distance x. Now there's a difference, or there are some additional note to consider if we are analyzing um, the uh, the interaction of the work and energy in curvilinear motion. So for a particle undergoing curvilinear motion, the work done is due to the gravity force, which is equal to the weight multiplied by the elevation. Now in our diagram right here, the displacement of the work does not necessarily mean the angular dis- the arc length from this position to this position, but rather it only consider the elevation, the change of elevation between these two positions from A and B, and that is if the work done is due to the gravity force. Since our system indicate does not indicate any applied force, so the movement of this particle is only due to the gravity force. So the work done is also due to this physical um, quantity, that is the gravity force. So the work done here is simply the product of the weight of this particle and the change in its elevation. This expression is also known as the change in the potential energy, because the formula for the potential energy, that is the energy due to the gravity force or the effect of the weight of the object. That is why we have this formula mgh. So m is the mass of the object, g is the Earth's acceleration due to gravity, and h is the height or the change in elevation of the object. Now the potential energy um, depends on some reference points. That is why we have initial and final positions. Okay, we are going to use these concepts in solving this problem. So first, we are going to use the work energy equation, and note that for curvilinear motion, the work done from point A to point B of the particle is equal to the change of its potential energy. That is the product of the weight and the elevation. Now, from the work energy equation, we have the total work done is equal to the change or the total change in its kinetic energy. So the total work done by gravity force is simply equal to the total change in its potential energy from this position to this position. Since we use the potential energy right here, so we will need an information for the elevation of these two positions. What will be the distance, the vertical distance from point A to point B. And since we are also dealing with the kinetic energy, so we need to know the final velocity of this particle at point B. So we have here VB. So VB, since this is a curvilinear motion, so the direction of the velocity right here is tangent to this circle at this point. Okay, so the potential energy, referring to the figure, that is equal to the weight of this particle multiplied by the change in the elevation, that is in delta y. So that's equal to 1/2 times mass times the difference of the squares of the final and the initial velocity of this particle. So we have here VB squared minus V naught squared. Next, the weight, as you can see, will be cancelled out on both sides of the equation. So leaving delta y is equal to 1 over 2g times VB squared minus V naught squared. Next, we are going to multiply this equation by 2g, both sides of the equation. So we have here 2g delta y is equals to this expression. Next, we are going to transpose the V naught squared towards the left. So we have this equation, and then rearranging. So we have V naught squared is equals to VB squared minus 2G delta Y. And then the next step is we are going to get an expression for the elevation in terms of the radius and some angles. So we will derive the expression for delta y. Now let's go back to our diagram. As you can see right here, we have a right triangle, this one. So this right triangle has a hypotenuse equal to the radius of the cylinder. Now the length of this side, since this side is adjacent to the angle, so this is the hypotenuse, which is the radius 8 cosine of 30 degrees. Now from the location of point A towards the center of the cylinder, this is equal to the radius r, which is 8. So therefore, our delta y is the difference of the radius and this side of the right triangle. That is why we have here delta y is equal to 8 minus 8 cosine of 30. Substituting this one, it will become, or the equation above becomes v naught squared is equal to vb squared minus 2g delta y. So we have here minus 2g times 8 minus 8 cosine of 30 degrees. Now, this is not yet the final formula in solving for the initial velocity. It's because we still need to know the value of the velocity at point B. So where are we going to get the value for our velocity at point B? Now, the next step is we are going to consider this assumption. So when the particle leaves the surface at B, so at this point, only the the only forces that interact are the weight of the particle, this one, which is directed downwards as shown. The next one is the reverse effective tangential force, which is directed towards top left. So we have here W over G times the tangential acceleration. And lastly, the centrifugal force, which is a force that is um, opposite to the centripetal force, which is directed towards the center. So this is our centrifugal force. This force is directed outward from the center of the circular motion. So we have here Wg times Vb squared all over r. And as you can see, there is no normal force since at this moment the particle is leaving the surface, which means that there is no contact that takes place. So from the problem statement, it is said that at this point, our particle is leaving the surface. So we don't have a normal reaction from our cylinder towards our particle. So these are the only forces that exist in this point. Now we can still resolve our weight into both normal and tangential. So the normal component of this weight, that is W cosine 30 degrees. Because if this is 30 degrees right here in geometry, this angle is also equal to 30 degrees. And next, the tangential component of our weight is W sine 30 degrees. Now, if we take summation of forces along the normal axis, this one right here, along the normal axis, so that is equal to 0, because in this diagram, although the object moves, since we already considered the uh, reverse effective forces, so this one is now under dynamic equilibrium. So we can now use the summation of forces equal to 0. Okay, because this is now in a state of dynamic equilibrium. So we take positive if the force is pointing in this direction. So okay, so we have the positive force, which is the centrifugal force. So we have W over G times VB squared all over R. That is equal to the negative force. So I already um, transpose this one on the other side. So we have W cosine 30 degrees. Now, as you can observe in this equation, the weight is common. So cancel that one out, leaving VB squared is equal to, then multiply the equation, or multiply both sides of the equation by GR. So you can have this expression on the right side of our equation. This is GR cosine 30 degrees. So we take the square root on both sides of the equation. We have VB is equal to the square root of GR cosine 30. Then substituting the values, our G is 32.2, the radius of the cylinder is 8, then cosine 30 degrees. And we have an approximate value of the velocity of B, or the velocity of the particle at point B, roughly equal to 14.96 FPS. Next, we are going to substitute the approximate value of our velocity B in this equation. So you have B naught is equal to the square root of VB squared minus 2G times 8 minus 8 cosine 30 degrees. So we have an approximate value. Sorry, this is only an approximate value of the initial velocity, roughly equal to 12.41 FPS. Next, um, the second requirement is to solve for x. Now, at this point, so our particle leaves with a velocity equal to VB. Then the angle of inclination of this velocity vector relative to this horizontal line is 30 degrees. Now, the angle in standard position is read as counterclockwise. But for this angle, this is 30 degrees in a clockwise direction. So if we are going to input this one on our equation, we will use the negative of this angle. Okay, now the motion that is being uh, the motion that is being performed by this um, particle from this position towards this point is projectile motion. So for a projectile, it has a height delta y, and then it has a range equal to delta x. So the delta x is the distance of the initial position of this particle, which is on the projectile motion's perspective, that is at this point, and then its final position is this point. So we have delta x, the horizontal distance from this point up to this point. Now we will add some useful information in order for us to know the distance of this x. Now for this right triangle, this side is equal to 8 sine 30. This one is also equal to this. So our x, therefore, is the sum of 8 sine 30 and the delta x from the projectile motion analysis. Now, this one right here, this side of a right triangle measures 8 cosine 30 degrees. So if we're going to analyze the geometry of our illustration, the delta y, which is the height of our projectile motion, is equal to the sum of the radius and 8 cosine 30 degrees. Now, we are now ready to solve for the distance x. So x, if we refer uh, from our illustration, so x is equal to the sum of um, this length, which is 8 sine 30, and the delta x. So use the general formula for projectile motion in order to solve for the delta x. So we have the general formula for the projectile motion. We have the height is equal to the range delta x tangent of the angle of inclination of its initial velocity. So we take the negative angle for this case. It's because the rotation of this angle is uh, clockwise. So we have negative 30 degrees minus g delta x squared all over 2 VB cosine negative 30 squared. Next, we will input the value for delta y. Now, this is negative. It's because the the direction of motion for this projectile is downward. So the downward path takes the negative sign. So we have negative 8 plus 8 cosine 30 degrees is equal to delta x tangent negative 30 minus 32.2 delta x squared all over 2 times. So the 14.936 right here is the approximate value of our velocity at point B, which is in our projectile motion analysis, this is the initial velocity. Then multiplied by the cosine of the negative 30 degrees. Next, we are going to simplify some terms. So on the left side, we have negative 14.928. Then for the tangent of negative 30, since tangent is an odd identity, so we have a negative 0.577 delta x. And then if we're going to simplify this term, it will become negative 0.09623 delta x squared. Now, as you can see, we have just generated a quadratic equation. This is quadratic equation because the variable delta x has a degree equal to 2. So we can use, or we can arrange this equation into this format, wherein we will start with the term that contains the highest degree, then followed by delta x and the constant. So if you already arrange your quadratic equation in this manner, then you are now ready to plug in the coefficients as well as the constant on the quadratic formula to solve for the value of our delta x, or the range of our projectile. So if you're going to input this one in your calculator or using the quadratic formula, you have a negative b plus minus square root of b squared minus 4ac all over 2a. You will arrive one of its root. So consider only the positive root, which is roughly equal to 9.8126 feet. So this is um the value of our delta x, or the range of our projectile. Now adding this one to our 8 sine 30 degrees will give us the distance of our x. So x is roughly equal to 13.81 feet, measured from the center of our cylinder towards the point where our particle strikes or hits the ground. Okay, let's proceed to the work energy equation applied for rotation. Now, for rotation, the work energy equation for rotation this time, sorry, I forgot to edit this one. So this should be rotation, is being derived from these two equations, these two important equations in dynamics. So these are the summation of moment. So if we have a resulting moment, we all know that it will produce uh, a uh, a twisting motion. So that is also equal to the inertia of the object multiplied by its angular acceleration alpha. So this is our first equation. Then the second one is a differential equation that relates the angular acceleration alpha times the differential angular displacement, that is uh, theta, then equal to the angular velocity times the differential angular velocity. We are going to manipulate these two equations in order to come up the work energy equation applied for rotation. So in order to do that, first we will solve for the angular acceleration from equation 2. So this one is the expression for the angular acceleration. Then we are going to substitute this expression to equation 1. As shown in this equation, we have the summation of moments is equal to the mass moment of inertia I times W dW over d theta. Next, we are going to multiply both sides of the equation by d theta. So we have summation moment times d theta is equal to IW dW. Then integrate both sides of the equation in order to get the general solution of this differential equation. So you will have this equation summation moment times d theta evaluated from 0 to the final angular displacement theta is equal to the integral of the mass moment of inertia I times W dW evaluated from the initial angular velocity towards the final angular velocity W. So let's simplify first the right side of our equation. So it will become 1 half IW squared from initial angular speed or angular velocity towards final angular velocity. So we will end up with this expression. So this is the formula for the kinetic energy applied for rotation. In other words, this is the rotational kinetic energy of a certain object. Now, if we consider that the moments from the summation moment acting on a body are constant, then the equation above becomes the summation of the constant moments multiplied by the angular displacement is equal to the rotational kinetic energy. So the rotational kinetic energy is a function of the mass moment of inertia of the object and its initial and final angular velocity. So the left side of our equation talks about the work for rotation. So for rotation, uh, it is the product of the moment and the angular displacement. So the moment should be, or uh, the moment, of course, must be, or the moment can be determined by taking the product of the force and the moment arm. And then the right side of our equation talks about the rotational kinetic energy. Let's say, okay, we're going to apply the work energy equation for rotation. We'll consider this circular object with outer radius r1 and it has an inner radius r2. And then suppose this object rotates at this point at the center of these two concentric circles, and let's say at the at the tip of this object we have an applied force Fa. So the moment arm of this applied force is equal to r1. So this force will of course produce a moment, and that moment will of course generate a rotation. Suppose this object already rotates at a at an angular velocity equal to w naught. So w naught is the initial angular velocity. So this is true. It's because we have an applied force here. Again, the applied force here produces a moment that is um, that is consequently will produce a rotational motion of our object. So this is now our direction of rotation. The direction or the direction of our moment, by the way, will also match again the direction of the resulting moment will also match the direction of our rotation. And suppose we also have an opposing moment. So we have a frictional force right here, FFF, with moment arm equal to R2. As you can see, if we take the moment of this frictional force, the direction of this moment is counterclockwise, whereas the applied moment is clockwise. So this frictional force opposes the moment of this applied force. That is why it will change the angular velocity of this object. So from initial angular velocity, to the final angular velocity W. So we will consider that this is the initial position of this particle on our body, and this is its final position of our particle on our body, and it has an angular displacement equal to theta. So the reason why its angular velocity uh, changes, it's because we have a retarding force right here, which is the frictional force. So for the rotation, the frictional force does a negative work in our body. Next, we will quantify the amount of mechanical work done on the system, so denoted by the small w. So the work done from the initial state 1 to the final state 2 is just equal to the summation of moment times the angular displacement. So same with the amount of mechanical work done for translation, we will also put some sign convention for rotation. So we take positive if the direction of the moment matches the direction of our rotation. So the direction of our rotation, as you can see from this diagram, is counterclockwise. So therefore, we will uh, make the force or the moment of that force positive if that force will give a clockwise moment. Okay, so in our object right here, the force that will give a positive moment, that is a clockwise moment, is the applied force Fa. So we have here Fa multiplied by its moment arm, that is equal to R1, then minus the frictional force. So the frictional force takes the negative sign. It's because this force will generate a counterclockwise moment, which is opposite to that of the applied force, and then multiplied by the angular displacement theta. Next, distribute the angular displacement theta, and you will arrive with the final expression for the work done from 1 to 2. Next, we will also quantify the change in the rotational kinetic energy in the system, so delta Ke, that is simply equal to 1/2 the mass moment of inertia I times the difference of the initial angular velocity and the final angular velocity. So we will combine these two concepts so that we can come up a work energy equation for this rotating object. So we have summation moment times theta is equal to 1/2 I w squared minus w naught squared. Substituting the expressions for both the left side and the right side, you will end up with this equation. So this equation models the work and energy interaction that exists on this rotating body. Now, how about for multi-body systems in which both the translational and rotational motion exist, just like this multi-body system right here. We have blocks A connected by a rope towards um, our cylinder C, and at the same time we have another block B that is connected to the cylinder C via a rope. So if we're going to analyze the system, the movement of A is translational because it only moves in the vertical direction, and same goes with our block P. So block P, the motion of this block is also translational. It's because it only moves in the vertical direction. For our cylinder C, uh, the type of motion that exists for this object is only rotational. So it only rotates with respect to its center. Now, for multi-body system with both translational and rotational motions, let's assume that for this type of system, the weight of A is greater than the weight of B, so if that is the case, we can set the direction of motion for this one. So the direction of motion for A, since A is heavier, so A will move downward. And then if A move downward, so this rope right here will cause a counterclockwise moment of our cylinder C, thereby making it uh, rotated. So it will rotate in a counterclockwise direction. So this is its direction of rotation, counterclockwise. And if the cylinder C rotates counterclockwise, so the block B will move downward in this direction. So this is its direction of motion. Next, we will consider the external forces that are present in the multi-body system. In this multi-body system, in order for us to know what are the forces that will produce a work for this system. So we have the weight of A, then we have the tension at A, but this is colored green, indicating that this is an internal force. So it will not cause any work for the system because um, this one will be canceled out throughout the process. Next, these two forces right here will cause a displacement, SA, and also it will cause a change in the velocity of RA, so from initial V naught A towards final VA. Next, we will consider the forces that exist in our cylinder C. So we have the TA. So TA is an internal force, so it will not be included in the calculation. And suppose we have a frictional force that exists between the bearings of our rotating cylinder and the internal surface of our rotating cylinder. So the frictional force that exists in our rotating cylinder is an external force. So therefore, this one will affect the amount of work done on the system as well as its available energy. Then we also have a tensile force right here, TB. And then for this rotating cylinder, so as it rotates in a counterclockwise direction, so its angular velocity changes from initial from this position. So we will just select a particle to represent its rotation. So we have from initial angular velocity W naught C towards final angular velocity W C. Then it covers an angular displacement equal to theta. Now we will proceed to the block B. So the available forces that exist are the weight of B and the tensile force TB. But the tensile force TB is an internal force, so it does not contribute any work or change in the um, total kinetic energy of the system. So these two forces will cause a displacement of our block B downward equal to SB, as well as some changes in its velocity. So from initial velocity V naught B towards final velocity VB. Next, we will use the work energy equation. So the total work done on the system, that is WT, is equal to the total change in its kinetic energy, so delta KET. Then for the total work done on the system, since we have three objects that are present in our multi-body system, which are the blocks A and B and the cylinder C, so we will add the work done by each of these objects. So that is, we have WA, sorry, I forgot again to edit this one. So this must be WB, this must be WC. So we have the work done on block A, then on block B, and then on the cylinder C. That is also equal to the change on the kinetic energy of these objects. So from A to C. Now, from this work energy equation, the work done at block A is equal to this expression. So we take summation forces times the displacement. So we will use this um, formula because the type of motion at A is translational. So we'll use summation of forces multiplied by the displacement. Now we will use the positive sign if the force is pointing downward. So pointing downward, it's because the direction of motion is downward. Now, for block A, we only have one force that exists that will cause work on our system, that is only the weight of A. So we have here WA times its displacement SA. Next, for the work at block B, so we have summation forces times S. Uh, we will take the positive if the force points downward or along the direction of motion. Now, the only force that will do work on our block B is WB times SB. Okay, because the WB is the only external force that will um, do some work. Okay, next, for the work done on our cylinder C, since its motion is rotational, so we will use summation moment times the angular displacement. So we take positive if the moment that is being produced is counterclockwise, which is same with the direction of our rotation. So the only external force that is present uh, in our cylinder C is the frictional force FF. And since this frictional force will produce an opposite moment, so we will use the negative sign. So we have negative FF times the radius of this frictional force, or the moment arm of this frictional force with respect to the center of rotation, times the angular displacement of our cylinder C. Next, for the change in the kinetic energy of our block A, so we will use this formula. This formula is from the kinetic energy for translation. Next, for B, the type of motion is translation, so we will use the same formula as A. And then finally, for the kinetic energy of our cylinder C, since it is rotating, so we will use this format. We have 1/2 times the mass moment of inertia of our cylinder C multiplied by the difference of the square of its final and initial angular velocity. So these are the formula that you are going to substitute to your work energy equation in order to model the work and energy interactions that exist in this multi-body system. So your takeaway for this slide is that um, if the object is in translational motion, so we will use the formula for translation. So that is, for kinetic, we use 1/2 mv squared. If the object is rotating, so we will use the formula for the kinetic energy, rotational kinetic energy, that is 1/2 I W squared. Okay. Now for rotational and translational, I have here a problem. So in the figure shown, determine the weight of body D that will permit body A to reach a downward velocity of 15 feet per second after moving 18 feet from rest. Determine also the total change in the kinetic energy of the system. So as you can see, our system comprises of four objects. The first one is block A, second one is our cylinder B, then the third one is our cylinder C, and lastly our block D. Now, next is we will identify the type of motion that exists for each of these objects. For block A, it will only move in a vertical motion, or on a vertical axis. Therefore, the type of motion that exists for block A is only translation. It's only translational. Now, for our cylinder B, it only rotates with respect to this center point. So the type of motion here is rotational. Same goes with our cylinder C. And then for our block D, it only moves in a vertical axis. So therefore, the type of motion that exists is translational. So we have two translational motions and two rotational motions. Now the given parameters are, we have the mass moment of inertia of our cylinder B, that's 24 foot-pound second squared. Then for our C, that's 36. Then it is also stated from the problem that the final velocity of our block A is 15 feet per second. Then it covers a displacement of 18 feet. Then its weight is 161 pounds. And in the problem also, you can read this phrase starting from rest. This means that the initial velocities of our A and D is equal to 0. And also the initial angular velocities of our cylinder B and C is also equal to 0. The requirements for this problem are first the weight of our block D, then the second one is the total change in the kinetic energy of the given system. The method to be used is still the work energy method for both translational and rotational motions, because we have two types of motion that exist for this multi-body system. Now in solving the weight of body D, that is WD, and the total change the kinetic energy of the system, delta KT. Now, if you are going to use the force inertia method, that is, you take summation of forces equals to mass times acceleration, that is by Newtonian method, you will still arrive the same answer as the work energy. But the advantage of using work energy class is that it will reduce the uh, the time of solving this one, because you're only using a single equation, that is work energy equation. But even if you're only using a single equation, that is the work energy equation, still you need some um, additional equations that will relate the displacement of these multi-body systems, because as you can observe, we have two types of equations that exist. So we want to relate the displacement in translation to the angular displacement in rotation. Same goes with the velocity. So you are going to relate the linear velocity in translation to the angular velocity in translation. So those are the additional formulas that are also needed in the work energy method. But don't worry, it's because those additional formulas are also part on the Newtonian method, that is the force inertia method. So if we are going to um if we are going to weigh those two methods, for me, if we are only to solve for the velocity and the weight, uh, it will be or I will uh, prefer the work energy method. It's because it will work, or you can get the final answer much faster compared to the force energy method. But the only drawback for the work energy method is that you cannot um, you cannot solve for the acceleration directly. So you will need some additional um, formula from the force inertia method. So if the problem requires you to solve for the acceleration, you can start your solution using the work energy method and then go back to the force inertia method. But if the problem only requires you to solve for the weight, the mass moment of inertia, or the velocity or displacement, you can use directly the work energy method, because this one is more efficient compared to the force inertia method. That is in terms of the amount of time that you are going to allocate when solving such problem. Now, let's continue for this problem. So the first step is to create an FBD of the system. This is our system again. Now let's start with the direction of motion. Now this is the direction of motion of our block A, which is downward. Now I refer my assumption from the problem statement, because in the problem statement, it was stated there that A attains a downward displacement equal to 12 feet. So the direction of motion for A is downward. Next, if the direction of motion is for A is downward, so the direction of rotation for our cylinder B is counterclockwise. And same goes with our cylinder C, counterclockwise as well. And then for D, if our cylinder C rotates counterclockwise, so it will pull this block D upwards. So therefore, the direction of motion for block D is upward. Next, we will indicate the external forces. So both external and internal forces in the work's perspective to each of the objects that are present in our multi-body system. Starting with block A. So in block A, we have two forces right here, the its weight and the tension. But in the calculation of the work, the tension is not included because this is an internal force of the system. Next, uh, these two forces will cause a displacement of this A that is downward equal to SA, and then it will also change its velocity. So from initial velocity V naught A towards final velocity VA. But from the problem statement, since it since the system starts from rest, so the initial velocity of block A is 0. Next, we will proceed to the cylinder B. So these are the forces that interacts our cylinder B aside from its weight. So we have the tension at A and the tension on the rope that connects our cylinder B and cylinder C. Next, we will also indicate the angular velocities. So the downward motion of our A, as well as those external forces, will also affect the rotational, the angular velocity of our cylinder B. So from its initial angular velocity W naught B towards its final angular velocity WB. So from initial to final, it covers an angular displacement equal to theta B. And then for our cylinder C, these are the external forces, the TD, the tension that exists on the rope that connects our cylinder C and D. We also have TCB. And then um, due to the effect of external forces, so the angular velocity of our cylinder C will also be affected. So from initial angular velocity W naught C towards the final angular velocity W C. And then from initial to final, it covers an angular displacement of theta C. And then the last one, we will consider the forces that exist on our block D. So these are the weight of the block D, which is to be determined, and then the tension on the rope that connects block D and C, labeled as TD. So with these two forces, it causes an upward displacement of our block D equal to SD, and it will also change its velocity, so from initial to final. And same with A, and same for the rest of these objects, the initial velocity of D is equal to 0. Next, we will use the work energy equation in order to solve for the weight of our block D. So the total work done on the system is equal to the total change in the kinetic energy in our multi-body system. So for the total work, these are comprises of the individual works done on each of the objects present in the multi-body system. So we have the work done at A or at block A, the work done at cylinder B, the work done at cylinder C, plus the work done on our block D, which is also equal to the sum of the individual change the kinetic energy for each of these objects. So we have for A, for B, for C, and for D. Next, for bodies B and C, no work is done since there are no external forces present. Uh, it was not also stated from the problem that we have some frictional forces on the bearings of these two rotating cylinders. So therefore, it does not have any mechanical work that exists. So the only mechanical work that are present are the work on block A and block D. So we have WA plus WD is equal to the total change the kinetic energies. Next, for WA, so the type of motion for block A is translational. So we will use this formula, summation of forces at A times the displacement at A, plus for block D, still in translational motion. So we use the summation of forces at D times the displacement at D. Now, don't forget to indicate the direction of or the sign convention right here. So positive for the case of A, uh, the force is positive if it is directed downward, which is along the direction of motion at A. And then for the sign convention of our block D, the force is positive if it is directed upwards, which is along the direction of motion for block D. Now, on the right side of our equation, so we have for the kinetic energy at A, that is in translation, so you're going to use this expression. Then for B, you're going to use this one, that is in terms of the mass moment of inertia times the angular velocity. It's because our cylinder B is rotating. Same goes with C, still rotating. And then for block D, we will use the kinetic energy formula for translation. Next, the system starts from rest, right? So this was also stated from the problem. Therefore, the initial velocities, the linear velocities for blocks A and B are equal to 0. And then for the rotating bodies, same also. So the initial velocity for cylinder B is equal to that of C, which is equal to 0. So substituting these values, we will end up with this equation. So for the um, work done on blocks A and D, so for block A, we have its weight and its displacement minus the weight of D. So why is it that uh, on the work done at block D, why is it that the weight now is negative? It's because the direction of the weight is opposite to the direction of motion. So on the total work of the system, the weight of D retards the motion of our A as well as the motion of these two cylinder. So it does a negative work on our multi-body system. Next, on the right side of our equation, so the only modifications that are being made here are the initial velocities. So the initial velocities become 0. So we only have this expression on the left side of our equation. So we have for A, and for B, for C, and for D. Next, uh, as you can observe in this equation, we don't have um, values for SD, for WB, WC, and BD. We only have values for our final velocity at A as well as the displacement at A. So therefore, as what I have told you earlier, that aside from the work energy equation, we still need additional equations that will quantify these parameters. It's because for the work energy equation alone, these are unknowns. So therefore, we need to solve um, the values for this one in order to solve for our ultimate unknown, which is the weight of the block D. That is why we will proceed to the next step, that is the determination of the relation between SA and SD. That is the displacement of A and the displacement of D. Now, in order to relate these two objects, as you can see from our multi-body system, the blocks A and D are very far from each other. So we need several formulas to relate these two. So in order to relate the displacement of these two objects, we need to relate first the motion of A relative to B, and then after that, the motion of B relative to C. Finally, the relation of motion of C relative to D. Now let's start with the um, the linear displacement that exists at the rope connecting A and B. So what I mean is this one. So the rope connecting A and B, the displacement of A can also be quantified as the product of the radius that connects this rope uh, from A to B. So that is 3 feet. This is the radius of this rope, or this point that connects our um, cylinder B and our block A. So at this point, the radius is 3 feet. So we have 3 times the angular displacement of our B. So we have theta B. Next, at the rope connecting B and C, so this one, B and C. So for this rope, they have the same um, linear displacement. So we have SB is equal to SC. Then SB, the linear displacement in this given radius is equal to 1.5 times the angular displacement of our cylinder B. So that is theta B. Then that is equal to um, the linear displacement of our particle at this point, that is equal to the radius, that's 3 feet. So the radius of this one multiplied by the angular displacement of our cylinder C. Next, at the rope connecting C and D, so this one, this rope from C to D, the linear displacement is equal to SD equals 2. So 2 here is the radius of the circle right here. So this circle is tangent to the rope that connects cylinder C and block D. So we have 2 times the angular displacement of C. Next, from this equation, we have theta C is equal to 1.5 theta B all over 3. So that is why right here we have this expression. Next, if you're going to multiply these two, we have the linear displacement of our block D is simply equal to the angular displacement of our cylinder B. And from this equation, we have the angular displacement of our cylinder B simply equal to SA over 3. That is why we have also this expression right here. Next, the the linear displacement of our D is just 1/3 of the linear displacement of our A. So we have just determined the relation between the displacement at blocks A and D. So for the displacement of D, that is just 1/3 that of A. So that's 1/3 of 18. So we have the displacement of D equal to 6 feet. So for every displacement made by A, there's only 1/3 of D. Okay? Or that's 3 times the displacement of D. So conversely, um, if A displaces 1 unit, so the corresponding displacement of D is 1/3 of the unit. Next, we will also determine the values of our velocity at D, the final velocity at D, the final angular velocity at cylinder B, and as well as at cylinder C. Now, we are going to differentiate the equation with respect to time of this formula that relates the linear velocity on the rope that connects block A and cylinder B. So we have SA equals 3 theta B. Differentiating both sides with respect to time. So for SA, we have the velocity at A equal to 3 times the angular velocity at B. Now, the angular velocity at B is simply 1/3 that of A. And since we already have a value for the velocity at A, the final, so the angular velocity at B is simply equal to 5 radian per second. Next, we will differentiate the equation with respect to time of this equation. So this equation relates the linear displacement of the rope that connects cylinder B and cylinder C. So this rope right here. So we have this expression or this equation 1.5 theta B is equal to 3 theta C, differentiating both sides of the equation with respect to time so that we can arrive an equation that relates the angular velocities. So we have 1.5 times the angular velocity at B is equal to 3 times the angular velocity at C. So we have the angular velocity at C is equal to 1.5 over 3 times the angular velocity at B. So the angular velocity at C is equal to 2.5 radian per second. And finally, differentiating the equation with respect to time for the linear displacement between D and A. So we have the linear displacement of D is simply 1/3 that of A. And if you're going to differentiate this one with respect to time, you also have this relation that the velocity of D is also 1/3 that of A. And since we already have a value for the velocity at A, so we have 1/3 times 15 that is equal to 5 feet per second. So this is the value of the final velocity at D. So now we already have values for WB, WC, WD, as well as the displacement. And we are now ready to solve for the weight of our black D. So solving for the weight of our black D, if we go back to our work energy equation, so this is our work energy equation, substituting those values. So the weight of A is 161. The displacement of our block A is 18 minus uh, the weight of D, so still unknown, then multiplied by the displacement of D. So we already get the value of this one, that is 1/3 of A, so that's 1/3 times 18, that is 6. Then equal to 1/2, the weight of A is 161 over the Earth's acceleration due to gravity. Then the velocity of A, the final velocity of A to be specific, is equal to 15 FPS, so 15 squared plus 1/2. Then the mass moment of inertia of B is 24. Then the final angular velocity of our cylinder B is 5 rad per second, so 5 squared plus for C, we have 1/2 times its mass moment of inertia, that's 36. Then multiplied by its final angular velocity, that's 2.5 rad per second square plus 1/2 times the unknown, which is the weight of our black D over the Earth's acceleration due to gravity multiplied by its velocity. So the velocity of D again is 1/3 that of A, so that's 1/3 of 15, that's 5, then square. Now simplifying further, so on the left side, these are the expression, or these are the terms, 2898 minus 6WD. And then on the right side of the equation, these are the values for each term. So 562.5 plus 300 plus 1125.5 plus 125 over 322 times the uh, weight of our black D. Now, combining these two terms right here, then dividing both sides by the coefficients of these two variable terms, we have this expression 2898 minus 562.5 minus 300 minus 112.5 all over 125 over 322 plus 6. If you're going to input this one in your calculator, you will come up an approximate value of the weight of our black D that is roughly equal to 301.02 pounds. So this is the weight that will cause a negative work on our multi-body system. If our black D is much lesser than to this value, let's say around 100 pounds, so the effect of that is that the final velocity of our block A will also increase, let's say higher than 15 feet per second. It's because if you're going to refer our work energy equation, the weight of our block D um, reduces the available work on the system. It does a negative work. So it's a retarding work from it's a retarding work of our multi-body system. And lastly, we will solve for the change in the kinetic energy, the total change in the kinetic energy of the system. So we have the total change the kinetic energy of the system is equal to the total work done in the system. Now you can use this formula. This is for the work done, or you can also use this formula. This is for the total change the kinetic energy of the system. In order to be efficient when solving this problem, select a formula that will give you much shorter time to compute. So in my case, I will choose the formula for the work done on the system. So we have WA, the weight of A times its displacement, minus the weight of D times its displacement. So we can now solve for this one because we already solved for the weight of D. So we have 161 times 18 minus 6 times the weight of D. So the weight of D is roughly 301.02 pounds. Simplifying this expression, you will arrive an approximate value of the total change the kinetic energy of this of the multi-body system, roughly equal to 1091.88 foot-pound. So this is the available energy present in the multi-body system, and this energy is the result of the work done on the system due to, first, the weight of our block A, and also the retarding work of our block D. That's why it is negative in here. Okay, so that's it for this video. I hope you learned something. Again, for the work and energy equation, this is another way of solving the parameters displacement, velocity, the weight, the mass moment of inertia of a given multi-body system under rotational and translational motions. So this is an alternative way of solving those parameters in a very short time compared to the conventional way using the Newtonian method, uh, which is also called as the force inertia method. But then again, if the problem requires you to solve for the internal forces like the tension, you may um, you may um, split the multi-body system into individual systems, and you can still apply the work and energy equation right there. But the only drawback for the work and energy equation is that you cannot um, solve for the acceleration of each objects, both the translational acceleration or the linear acceleration and the angular acceleration. So you still need the force inertia method in order to solve those those parameters that cannot be solved in the work energy uh, method. Okay, so if the problem only requires you to solve for the velocity and the displacement, um, or the weight or the mass moment of inertia, so I will recommend you to use the work and energy equation because it is much faster compared to the force inertia method. Okay, so thank you for watching, and may God bless you.